pop up. All right, give me 1 second, guys. All right, people. Afternoon session. Let's get cracking with this one. Thank you, Suclean. Got your question. I've got a few questions to do at the moment. Let me just adjust a couple of adjust things. All right, here we go. So the questions. Oh, actually, you guys can't see anything because my screen is still black. All right, let's just fix that. Okay, so what we're going to go through is some of the questions I left off from yesterday, guys. So all of these at the moment are all excellence questions. So I do apologize if you are looking for achieved in merit questions. Yeah, this is probably not to be, but it's all right. You know, you can just still watch because most of the excellence questions, if you attempt, we will be going through. What do you call it? Most of the excellence questions can be converted as achieved or merit questions. Leah, I think I've got one complex number question here so far, but mostly differentiation, integration. Yeah, I've got, my first question was like a complex number one. But Leah, if you got a complex question that's really bugging you, an excellence question, just chuck it up because I haven't actually seen a complex number question in excellence in a while. So wouldn't mind doing it for a change. All right, Dampier, we're going with your first question, which is, I think, 2015 3E, I believe. Did we do this yesterday? No, this is not 2015. 2013, sorry. 2013 3E. In the start of this chat, Dampier, that's what you requested. I think that was the first message today from you. But anyway, I think it's a really good question to kind of work through anyway, because it is a triple threat, as I call it, a triple threat rate of change question. All right, I will put that down 2014 as well. Just have to wait for a while, Dampier, because we've got to go through the other questions and then I'll come back to it. 2014 3E. Was it 2014? All right. Anyway, so have I done this question before? I can't remember because I've just been doing like random questions. Or do you guys want me to go through this question? This is light question. Okay, I will assume that it's a yes and that you guys, yeah, we'll go through this, all right? Okay, so kind of first things to understand with this question is that we've got a rate of change question here. So as I said to you guys before, when I used to do my rate of change questions, start extracting the information out and see what it is that you have and then try and figure out how we can actually manipulate the equations to get what we want. So the first thing that we can extract the information is that dv dt equals to 300. (2016 3E). Angela, I've already done that question, 2016 3E. I did it yesterday's tutorial, last night's tutorial. All right, next thing it goes, material of this balloon is limited strength. Balloon will burst when its surface area reaches 7,500. So this is the thing. When surface area reaches 7,500, balloon pops. And then the question's asking, find the rate at which the surface area of the balloon is increasing when it reaches bursting point. All right, so what we're looking for is dSA of dt is what we're looking for. So now with rate of change question, remember that this is what you're looking for, and let's actually see what we have. What we have right now is dv dt. All right. Now we also know that we have a sphere. So we have a sphere, and we know that the sphere has a volume formula, and we also know that the sphere has a surface area formula. And of course, with the sphere, you're always working with radius, right? So we know that with the volume formula, we could get dv dr, and with the surface area, we could actually get dsa of dr. All right, so what we've got to try and figure out is how we're going to put all these three green things together in such a way that we end up with the pink thing. I hope that actually makes sense. I know I kind of went randomly with letters, but so the way it works is like this. So we're going to put dsa over dt equals, because we're trying to figure out what we need to multiply it by. So dv dt multiplied by dr dv multiplied by dsa over dr. Because by doing this, what you're effectively doing is getting rid of dv, and also you're getting rid of dr, and you're left with the dsa on the numerator, and you've got dt in the denominator. Now this part here is super important, because if you get this part, then this entire excellence questions is literally just like substituting and solving. That's all. Sorry, differentiating, substituting and solving. So going now, if you guys actually forgotten your formula sheet, I'm just gonna grab the formula sheet. Give me a second. My formula sheet, calculus. Is it actually given for sphere for you guys? Tell me it is. Yes, it is. Okay, awesome. So you guys actually get this part in your formula sheet, which I'm just going to chuck up. Give me 1 second. So we can kind of see that one that we're looking for is the sphere one. So that's the one I'm going to actually use. So Robert, I think going back to this, man, just write down what you have and what you're looking for. So if you look at it, this green part right here is what you're starting out with. And then the pink part is what you're looking for. And I think if you write your equation like something like in this green box, you can kind of try and figure out. Yeah, Robert, it'll always be over some rate. All right. Whenever you see rate of change questions, it's either going to be like 2 of the rates that are working together or 3 of them working together. And if 3 of them are working together, you're definitely looking at an excellence question. All right. So I'm going to take my volume equation for a sphere, which is 4/3 pi r cubed. And my surface area equation is equal to 4 pi r squared. So when I differentiate this, I'm going to get 4 pi r squared. And when I differentiate surface area, I'm going to get 8 pi r. Remember that pi is actually a constant, guys. So it's a number. So therefore, we don't really have to worry about kind of like getting rid of it or anything like that. So from here, we can actually set up our equation, because dsa dt equals dv dt is 300, dr dv, so that's going to be 1 over 4 pi r squared, multiplied by dsa dr, which is 8 pi r. So just to kind of, I'm running out of colored pens here, but so that's your dv dr flipped upside down, and that's your dsa dr. Cool. Now, it actually says we need to find the surface area of the balloon is increasing when it reaches bursting point. So we actually know at what radius the burst, what is the radius when the burst happens. So we know that surface area is equal to 7,500. So we're going to put 4 pi r squared equals 7,500, and r squared is equal to 7,500 divided by 4 pi, and r is equal to square root of 7,500 over 4 pi. Where's my pi? So our radius, what do we got radius as? 24.43. And because radius is 24.43, we substitute it into our DSA dt formula, which is 300. I'm going to simplify this, guys, because I can. It just makes it easy. Get rid of the pi, get rid of 1r and r, get rid of 8 and 4 is 2. So that's going to be 600 in the numerator divided by r. So we're going to get 600 divided by 24.43, which equals to 24.56. And that's surface area over time. So surface area is centimeters squared, time is in seconds. So we can just leave it like that. Now, it doesn't say anything about units required, but for excellence, you need correct solution along with correct expressions. So basically for excellence, you need this, you need this, you need this, and dA dt. Oh, and this. So there's about 4 parts that you need to get correctly. Jasper Mace. I'll have a look, Jasper. But I've got a few other questions that I need to work through at the moment. Did you guys send it to me now, Kian? Oh yeah, I see what you got. Yeah, Kian, I've got that question today. Unless you sent me another question. Oh, is that the complex number one that you guys sending me? Integration 2017 1E. All right, I'll put it on that list, Emily. Might have to be doing it tonight, but yeah, we'll see. Hey Kian, which paper is that from? The P and Q. Z is a complex root of this equation. So you want an expression for P in terms of A and B. I'm just wondering, Kian, you guys can just substitute Z as A plus BI. Okay, I'll have a look at it later, guys. Okay, I'll have a look at it. I think I know where I might be able to find it. Okay, so are we okay with this question here, this differentiation question? Because I'm going to jump to an integration, any of the 2015 complex E questions. Okay, Leah, I'm going to put that up there after Kian's complex question. What I'll do is I'll actually put Kian's question up there, and then I'll go through the complex 2015 excellence. We good with this one? So if you guys want to have a look at Kian's question, which is a complex number question, it's just here. I'm just going to leave it for you guys for like a couple of seconds if you want to have a look at it and work on it while I'm going to try and come back to that question today, guys. So Kian, you said it was in your mocks this year. Let me just see if I can find it, but no, I'm getting distracted. I'm going to go back to this other question. Which one am I doing next? I'm going to do one more differentiation or integration, folks. Which one should we do? Because I've got two of each. Okay, I get it. Differentiation it is. Next differentiation question is with similar triangles, which I picked up this one here. I'm not sure which paper this is from. But this was the question that I picked up. And then I'll do Kian. I think I've got your question next coming up for. Okay, you guys got two choices to make right now. Either you want this question here, which is using, I believe it might be using similar triangles, or do you want to do this question here? So, option A, or the other one that we just saw before. They're both differentiation questions. No worries, Ria, you're welcome. Yeah, so you got the SaltWorks question. Actually, no, I've got to do this question here, guys, the one up on the screen, because Kian did just send me this question a while back. So let's actually get that done. All right, so what we've got here is blah, blah, blah. Okay, slant of a cone. Find at the rate which slant height is increasing when the radius of the cone is 10. So slant height is, let me just redo this whole thing again. What do these guys have done? This is going to be another kind of, I can feel it, it's a rate of change question, but it's going to be like another triple thread, I believe, but let's see how this actually works out. So the first thing we've got is we've got conveyor belt, which is going to be putting 2 meters per cubed, so that's going to be dv dt equals to 2. Yeah, I can't remember. No, I think I actually missed this one, Daniel, last time. I'm sure I didn't actually do this. That's why I copied it again. Okay, so next thing is find the rate at which the slant height is increasing when the radius of the cone is 10 meters. Now, just to kind of clarify things here, that's the height, and then that's the slant height. So I'm actually going to use S for the slant height. So the question's actually asking us, what is ds dt when r is equal to 10? Okay, one other thing that we also have is this cone also will have a radius, and the radius is going to be there. We know that we're working with a cone, so we need the cone's formula for the volume for a cone, and I think, sorry, I just put it here, volume of a cone, 1/3 pi r squared h. So I'm going to get out of this again. Okay, so this is all the information that I have right now. So if I look at it, I want to actually work out what ds dt is. I've been given dv dt. I know that I've got volume of a cone, which means I can actually figure out what dv dr is. So I can put this upside down as dr dv. So the last thing that's actually remaining in the numerator, I need to have ds, and in the denominator I need to have dr. So what I gotta do is I actually have to write S in terms of R. All right. I think that's what you guys need to realize. And also, so here's a couple of things. I need to write S in terms of R. So S as something of R. And also in the previous box here, I need to actually figure out a way to get rid of this H, because I'm actually differentiating with respect to R. Okay, so those are like the couple of things that you guys need to notice. Cool. Yes, Dave, I think it's in my list here somewhere, so we'll just kind of go through it slowly, all right? So the first thing is, let's actually get rid of H. All right. So to get rid of H, what we can do is we can actually rewrite H in terms of R. Because what I'm talking about is looking at that triangle. So let's actually get rid of H first. So we're going to use this triangle that we can see here, where this is R, this is S, this is 30 degrees, and this is H. Now if you think about it, if we're going to use opposite and adjacent, because we want to write H in terms of R, we can actually say that tan 30 equals opposite over adjacent, or tan 30 equals H over R. Or in other words, we can actually say H is equal to R tan 30. Cool. So now that we've done that, we can actually figure out what dV/dr is, because we can say volume of the cone is 1/3 pi r squared h. But because h, we've just proved that h is equal to r tan 30, we can actually write this as 1/3 pi r squared times r tan 30. So expanding the bracket out, we're going to get 1/3 pi r cubed tan 30. And then when we differentiate it, we're going to get dV/dr, which equals pi r squared tan 30. Now tan 30 is a number, so I really don't need to worry about it too much. All right, are we okay with that, guys, what I've done so far? Now we can leave it as, just leave it as it is, and then kind of come back to it at the end. All right, the next thing is we need S in terms of R. So if we look at S in terms of R, we're still going to be doing the same triangle. We've got S and R, and then this is 30 degrees. So if you look at it, that's going to be adjacent and hypotenuse. So we can say cos 30 equals adjacent over hypotenuse. So cos 30 equals r over s, and then s is equal to r over cos 30. So now we've got s in terms of r, which means we can differentiate it. When we differentiate ds dr, remember cos 30 is a number. So all we're going to get is, when we differentiate it, we're going to get 1 over cos 30. Overrated, I'm probably out of time for questions for this stream, but I'm going to be back at 8:30, so if you actually send it to me, I might have some time to do it. Robert, you with me so far? What we've done with ds/dr? Cool. So if we're good, sweet. So I think we've got everything that we need, because now we can go in and do this entire little formula that we have there. Because what we've got is, I'm just going to write that down first. ds dt equals dv dt multiplied by dr dv multiplied by ds dr. So dv dt was 2. dr dv is 1 over pi r squared tan 30 multiplied by ds dr, which is 1 over cos 30. So just to recap, that's where my dv dr comes from. But I remember I've got to flip it upside down, and then I've got my ds dr, which comes from there. And also the question is asking me, what is s over t when r is equal to 10? So I just need to substitute r as 10, and I've got 1 over pi 10 squared tan 30 times 1 over cos 30. Jeffrey, I'm sure there's other ways to do it, but yeah, I'm not sure, man. Like, this is the one method I know how to do. Cool. So just chuck this in the calculator and you're pretty much good to go. So we've got 2 divided by pi times 10 squared times tan 30 times cos 30. And just make sure your calculator is in radians. That's fine. So what am I missing here? 2 divided by I'm going to try that again because something's not right there. Oh, I put 30. Whoops. I know what my mistake is. I know what my mistake. Yep, I was just wondering that. Shift setup. It's got to be in degrees. Thank you. Put that back in degrees. There's my answer. 0.0127. Slant. So that's going to be meters, and time is going to be in seconds. So meters per second. Really? Did I do this question? I really can't remember, man. Like, sometimes you just do these questions again and again and you like just kind of forget. So okay, thank you, Osteo. Where did I do it? Must be in differentiation then. Ah, you gotta be kidding me. I did it on 20th of October, so that was a while ago. There we go. So I think I did pretty much. Yep, there we go. I need to find a way to categorize my questions so that. Yeah, I've got to figure out a way to actually do this in a much more efficient way next year. That's all right. 2017 differentiation 3E. I thought I did that 2017. 3E. Am I going to go to integration, or shall I? Actually, no, I'm going to go to a complex number question because the guys that sent me this question looks very interesting. This one here. Man, that was 20 minutes. We could have done some on another question. Okay, give me 2 minutes, guys. I just want to try and have a play with this first before I start to explain it. 3E. So let me just figure it out. So this is the question we're going to be looking at next. This looks like. X is 4 to whoever keeps asking that question. No, that's not it. Surely not this one. 578, 577. Come on, where did these guys get this question from? Gotcha. So they want P in terms of A and B. Okay, all right, got it. Oh, is that your final answer, Gia? All right, guys, so let's have a look at this question. All right, now this question here, when I first looked at it, I was like, I kind of had a different approach to it, but that is an extremely long way. But even though it looks kind of ugly at the moment, trust me, it's actually not too bad, this question, compared to some of the ones that we've actually done before. So remember that whenever you have a complex root, right, the conjugate root of it is also a solution. So in other words, if I put down z is equal to a plus bi, then another one of these solutions is, because it's a z cubed, right? So we can say that z is, there's going to be a second one, which is going to be a minus bi. Because that's what the conjugate root theorem is. Yeah. And then we don't know what our third little item is going to be, so we're going to put that as something else. In this case, I know you're not going to like it, but I'm going to put down the letter K, just for the hell of it. Because what I'm going to say is like this, because remember, when you have like three solutions, you can, you know how, like, just to show you guys, if I have like x is equal to 2, 3, and 5, for example, then you know the cubic is going to look like this. X minus 2, x minus 3, and let's say this was negative 5, for example, then this would become x plus 5. All right, so that's what it's going to look like if it's a cubic and it has three solutions. So right now we do have a cubic because this is z cubed. So what we can say is, we can actually say z minus a plus bi multiplied by z minus a minus bi and multiplied by z minus k is equal to 0. Okay, now the next thing is you, and this is where you gotta get used to some of these tricks and tips. All right, the thing that you need to notice here is you collect all the real parts and imaginary parts in these two brackets. All right, so what I'm going to do is I'm going to rewrite this as z minus a plus bi, and then multiplied by z minus a, what have we got, minus bi again. What have I missed here? Oh no, there's a minus there. Sorry, I've got to take that minus bi, and then this becomes plus bi. Yep, got it. Thank you, Dampier. Okay, and now here's the thing, guys. What you don't want to be doing is, now any other person would be thinking, oh man, this is going to be one super ugly looking expanding this bracket, especially with 3 elements. But it's when you actually start to look at a question and recognize patterns. And what I generally tend to do is, like, I like to put brackets around my real parts and put brackets around my imaginary parts. So what I mean by that is something like this. You can do z minus a minus bi, and then z minus a plus bi. And if you guys look at this part here, this is very similar to saying, I hope you guys can see here, I'm coloring it in different ways so that you guys can actually try and track it, because it's actually difference of 2 squares. So can you guys see that? How yeah, this is an excellence, but I'm surprised it's an excellence because it's actually not too bad. It's just recognizing what you need to actually do. So what's happening is that when I do this multiplied by this, I'm going to get z minus a squared. And remember, when I multiply this and these two things, they're going to cancel out each other, and we're left over with the final term, which is going to be minus b squared I squared. And this is all getting multiplied by z minus k to equals to 0. So we can simplify this as z minus a squared plus b squared, because remember, I squared is equal to -1, and we left with this so far. And now at this point, you don't have a choice. You've actually got to expand the bracket and just kind of expand the whole thing again. So we're going to do z minus a squared first, which is z squared minus 2az plus a squared plus b squared multiplied by z minus k, and this is equal to 0. Sorry, not equals to 0. What am I doing? Just expanding it. Let's get there. We're just going to expand it for now, and I'll show you what it equals to later on, so it kind of makes sense. All right, so once we got this part, we continue expanding. All right, we do not have a choice here. We just have to expand it. But again, I'm going to make things a little bit easier again, because what I've got here is z 2az, and I'm going to put a little bracket around a squared plus b squared, just because, trust me, it'll make sense later on why we do that. But so I've got z squared times z, which is z cubed, z squared times k, which is minus k z squared. Then I've got minus 2az squared. And then I've got plus 2akz plus a squared plus b squared times z minus a squared plus b squared times k. Let me know if you guys are okay with what I've done there so far. Because all I've done is I've just expanded the brackets out. Okay. Now comes a couple of trick parts here, which you gotta kind of know. It actually tells you guys that where P and Q are real, okay, that's fine. We also know that there is actually no z squared. Can you guys see how there's like no z squared here? So it's actually 0 z squared. And because z squared is actually 0, we can say that negative k and minus 2a is going to equal 0. So we can actually write that down here. Negative k minus 2a equals to 0, because the coefficient of z squared is actually 0. And because of that, what we can actually say now is What have I messed up here? Have I got that right so far? I just want to double check that, guys, because I'm missing something. Alpha minus 2a. Where did I get the negative k? Okay. That's alright. I should have actually put that as plus. Would it matter? It shouldn't matter. What I can actually do is I can actually put down k is equal to negative 2a. So I'm just rearranging. Now this is not a merit, guys, I can tell you that much. Have I missed something? No, I've not missed something. I think I know where my mistake is. What did you get? K equals negative 2a. Yeah. Now I think what we negative is going to be a positive number. Now I'm just thinking my original root there. I think it's got to be z plus k. The reason it has to be z plus k is because, okay, I'm just going to go back and do one little change, guys, which is going to stuff up my entire question, but it shouldn't be too bad. But will would it matter? I don't think it'll matter because I can still, it's an inverse. Okay, I'm going to try and do this anyway. Let's just see what happens. What else we've got? Yeah, let's see what happens. Okay, it's all right. So that red part there is my zero part, right? That's figured out. Now if I look at my original equation, which is here, is z cubed plus pz plus q. Now if I look at the next part, the coefficient of z is equal to p, which is this and this. So we can actually say that p equals a squared plus b squared plus 2ak. Now it's still going to work out, so it's fine. And because we figured out that k is equal to negative 2a, so we actually said that k equals negative 2a, we can substitute k in here. And what's going to equal is a squared plus b squared plus 2a negative 2a. Which means we're going to get p is equal to a squared plus b squared minus 4a squared. Simplifying this, we get p is equal to a squared b squared minus 3a squared. And I think the original question asked for expression of p in terms of a and b, which we have actually done. Noor, tan 30, it's a number, you don't differentiate it. If it's tan x, then you differentiate it to sec squared theta. Indy, it's all about just kind of messing around with it. I mean, like, ideally with excellence questions, I say this to people, you want to spend about 10 minutes on it, but if any more, and that's something that so I mean, like, the way it works is like you got 3 excellence questions, right? 20 minutes each. So that means if you struggling with an excellence question after 10 minutes, I would make sure I stop the excellence question, go and do question C and D, which should be like the 2 merit questions. All right, that way at least you get an M6 from that question rather than not attempting it at all. Dave, possibly, yes, you could do that as well. You could do simultaneous equation. So there is another way of doing this question as well. But I don't know, man, like, I'm just... Yeah, so going back to your kind of point, Indy, I always say this, you know, with excellence questions, is that you break down each paper. Like if you're doing 3 externals, so let's say you get 1 hour for the complex numbers, then if you are stuck in the excellence question after 10 minutes, I mean, these are for people that are trying to aim for excellence, but if you're trying to aim for like achieve merit, then I'd actually go forward. So I'd actually work at the achieve question first, then the merit question, and then attempt the excellence question. But if you guys are trying to aim for excellence, then I would say go to that final question and try and attempt it. But after 10 minutes, if you can't do it, then go back and do those 2 merit questions to try and get the maximum grade possible for that question. Dave, Jacob, I'd be quite curious to see what... Yes, Indie Bear, it is possible. And that's kind of the reason why I'm spending so much time on excellence questions, because not because you can all, like, you know, some people will just be brave and attempt just excellence questions, but majority of the ideas that you cover for the whole paper gets covered in like that one question. All right. So are we okay with that complex number question? And I know a few people have asked me, do we want to keep doing a couple of more complex numbers? Bailey, that is on my list, man. Yeah, so you can get an E7 with like 1 minor error. So even if you go like all the way to K minus 2A and you make a little mistake, you can still get like E7 for that. Oh, the one I skipped. So are you talking about this one here? The cylinder inside the cone. Okay, this one I'm gonna do it pretty quickly, guys, because it's not too bad. So what we're trying to find is what it must be the radius of the cylinder to give the cylinder the maximum volume, right? Is there osteo? Did I do it before? Oh, is it? Okay. So there we go, guys. I think there is from the daily playlist that question's already there, the cylinder one, because I remember doing this a few years back. So I think, let me just find it, see if I've actually got a video for it, because for those of you guys that have kind of been asking me for it for a while, can just have a look at it later. So calculus daily, I think it was excellence question. Was it 2015 2E? Oh, that's algebra integration. Differentiation 1E. No, that's different. Maximum volume, that's a different question. Oh, yep, I see where the question is. Okay, give me a second, guys. I'll just put a link for this question, so if you guys want to watch it. So basically, this video here, copy. I'll just put a link up there, guys. That has 2014 excellence questions, which is 3. So basically it has all these questions. Cool. Those are the ones, those are the 2014 ones. So we don't have to waste any time on that one. Hey, look, I've had an integration question. So this integration question, are we going back to complex numbers? Because I know some people asked me for complex numbers in 2015. 2015, was it, Leah? Did you ask me 2015? Okay, give me a second. I'm just going to pull out the 2015 complex number questions and I'll go through those three. Sporadic all over the place today. Uh, 2015, did she say, Leah? Oh, I thought I did 2015 one as well before. (2015) question 2E or 2E. Is that 2E, Leah? Yeah, we'll do 2E and 3 quickly. I'm going to come back to differentiation and integration soon, guys. Give me a second. I know this is one of my kind of this annoying question, but really good question to understand how to do this, because if it does come up, then you can pretty much be guaranteed to get a nice E for this. And even if you don't understand how to do it, you can actually do some parts of it to actually get a good grade for this. Okay, so this is the next question we're doing. This is from 2015. 2E, complex numbers. Okay, so to get this question here, what it's asking is, it's asking us to actually do a Cartesian equation for this locus, yeah, blah, blah, blah. The only thing that we know is that the argument is equal to pi over 4. Now guys, something to remember. When you have argument of pi over 4, now remember, pi over 4 is actually 45 degrees, right? Where's my pen not working? The worst time for the pen to actually shut down. Give me 1 second, guys. That would really suck, that if the battery runs out of my pen right now. No, we're back. Cool. So always remember, when you're actually dealing with pi over 4, that's the same thing as saying 45 degrees. So if you think about it, 45 degrees, yes, this one, you're absolutely right, Jacob, that's what you're going to be doing in this case. Because it's 45 degrees, you can actually say that real part is actually equal to the imaginary part. All right, so all you have to do with z minus 2 over z plus 5 is write it in such a way you can actually get the real part equal to the imaginary part, and you should be good to go. So we're going to write down that z is equal to something like a plus bi. So if we have the look at the complex number now, we're going to get a plus bi minus 2 over a plus bi plus 5. So this is the complex number right now. So what we got to do is we've got to actually rationalize the denominator. All right, so what I'm going to do is I'm going to put all the real parts together. So it's a minus 2 plus bi divided by a plus 5 plus bi. So I'm going to multiply it by a plus 5 minus bi, and then the numerator by a plus 5 minus bi. Depends on the question, Nora. All right, so once we have that, all you got to do, Leah, is actually just expand the brackets out. That's basically it. But what we have is, unfortunately, one ugly looking equation. So you are going to get something like, with the numerator, I've got to do a times a. It's going to be long, so just be patient. A times a is a squared, then 5a minus abi. Then I've got minus 2a minus 10 plus 2bi. Then I've got plus abi plus 5bi minus b squared I squared. And the whole thing is divided by a plus 5 squared minus b squared I squared. So let's actually start getting rid of some things here. So minus abi and plus abi disappear. And what else do I have? Nope, that's all I have. So I've got a squared plus 3a minus 10 plus 7bi plus b squared. Because I squared is -1, and -1 times -b squared is equal to b squared. And that whole thing is divided by a plus 5 squared plus b squared. That's it. We're pretty much done here, Hashil. I know it looks terrible, but we're done. Because look, we need to actually show that the real part is equal to imaginary, right? So in this case, if you look at the real part, that's real, that's real, that's real, and then this is real. And imaginary is going to be the purple part, which is just the 7. So if we write this as an equation, we're going to get a squared plus 3a plus b squared minus 10 equals 7. And the last magic trick that I have for you guys is, because you're looking for a Cartesian plane, we should have really, instead of writing it as a plus bi, we should have written it as x plus iy. Because if we did it with x plus iy, we're going to get x squared plus 3x plus y squared minus 10 equals 7. Okay, so I know that the few people that have kind of going a bit mental of why the real is equal to imaginary, because the important part is this part right here. See how it says pi over 4? So if I take a complex number like this, take a complex number but z equals to 4 plus 4i. Because that's 4 and then that's positive 4, your complex number is going to be here. And what you've got is this distance is 4 and this distance is 4. What you have is an isosceles triangle. And because it's an isosceles triangle, that's why you know that the real part is equal to imaginary part. As for the denominator, I know somebody asked me this. If I say 3 over 10 plus 4 over 10i, actually, like, let's say x over 10i, right? And if I say that the argument for this is equal to 45 degrees, then we can say 3 over 10 equals x over 10. But really, we don't really need to worry about the denominator at all, so we can just say x is equal to 3. Okay, Leah, so Cartesian equation is just like this equation that you've just done. It is actually a circle, I believe. So I'm just going to show you guys what that equation actually looks like on, let me just see. So we got x squared plus 3x it's going to be a circle because it's x squared and y squared. Just give me a second, guys. I just need to figure out where to put this image. There we go. That's a very tiny image, but so all it is, it's just a circle. Yes, Indie Bear, that's what it is. Cartesian is basically Cartesian plane. Remember, Cartesian plane is just like x and y axis. So all they're really asking for is just the equation of the locus, that's all, yeah, as you're saying, Eugene. So guys, I mean, if you think about this question, right, like even if you don't know the, if you see a locus question and you've got no idea of what to do, the first thing you do is do this part here. Put z is equal to x plus iy and just start substituting it and start solving it. Dampier, in this question, it doesn't actually ask you to describe the equation, so you don't actually have to worry about it. But I'm going to show you guys that extra step. Well, actually, I'm going to show you guys that little extra step here, just to show you where the center of the circle is and what the radius is. So to do that, it's basically this. You got x squared plus 3x plus y squared equals 17. Okay, that's not a problem, Dampier. So I think I just want to double check whether we can actually do this in the graphics calculator, because it would save us a hell of a lot of time. Let me just check. Conics, where's my circle at? Yeah, there you go. So if you go into your I don't know if this will actually work out R, but we can try it out. I've never done it before, but just chuck that in there, and you've got a value is going to be 1, a y squared's value is 1, 3, d, oh no, hang on, a is 1, b is 1, c is 3, no, sorry, b is 3, c, y, I don't have any 1, d is minus 17. Okay, so there we go. Actually, Dampier, you can actually do that, because that actually gives you what the radius is and also where the center is. Okay guys, I'm going to show you guys how to do this from step by step. So if you want to have a look at it, so I know sometimes they actually ask you guys what type of shape is this, and you can actually use the conics function in your graphics calculator to pull out the radius and the center, because what it does is it actually completes the square and tells you what it is. So basically, go to conics. So on your graphics calculator, go to conics, and you want to go into the picture that looks like a circle, and I think it's at the bottom, particularly written like this equation here, just like how it's written in written for you guys. So at this point, you look at the coefficient of x squared and coefficient of y squared, it's both 1. So then your b value is the coefficient of x, so in this case it's 3. We don't have a coefficient of y because we don't really have any y, so c is going to equal to 0. And the number by itself is minus 17, so we're going to put d as minus 17, because we need to make sure that this equation equals to 0. And if you draw, that's the shape you get. And if you click on G-solve, it actually tells you where your center is and where your radius is. So radius is 4.38, and the center has got to be at 1.50, I think. There we go, 1.50, and it's very similar to my graph as well on Desmos. So that's just that extra part. Yeah, I didn't know that you could do it. I actually just learned that just now, just as you guys did. Why is Why is 7b not included? Oh, that's a good point. Did I make a mistake? Yep, I did. Thank you. I thought you guys were talking about something else. Yep, I have made a mistake. That should be 7b. You guys are absolutely right. That's all right. So that should be 7b. If it's 7b, then let's see what happens. So nothing else. This just becomes 7y and 7y. Sorry, I kind of missed all of that. So then this just becomes x squared plus 3x plus y squared minus 7y minus 10 equals to 0. So let's have a look at what this looks like. I thought you guys were talking about the level 2 question with question 7 or something like that. So that's why I was getting distracted there. That's okay. Let's go back and fix this. So we're going to get a value is 1, b value is 3, negative 7, d is negative 10. Let's draw that. There we go. G-solve radius. So we're getting radius of 4.94. And our center is going to be at negative 1.5, 3.5. Now, honestly, I thought you guys were discussing the exam questions for level 2 with questions something with 7 or 7b. That's why I missed that completely. Apologies. Yeah, Johnny, I'll spend some time talking to you guys about level 2 exam later on, man. But all right, so that's complex number 2e. We're gonna go to 3e next. Sorry, Johnny, these guys have got their crunch time exams tomorrow. Some of them are like university entrance, so let's just go through these guys and then I'll come back to that. All right. Let's check out question 3e. Okay, so 3e is a 2-part question. Let's actually do the first part. Correct values of Z1. So where's the second part of the question? Let P be the root. Okay, here we go. Now, for those of you guys that have actually been attending my tutorials, you should see that part 1 and just be like, man, this is just, why can't every calculus question be like this? There we go. So this is 2015 3E. Alright guys, so let's actually do the first part of this question. Eugene, it's a double part question, this one. The first part is worth merit and the second part is worth excellence, Eugene. Robert, I'm finishing. This is the last complex number question I'll be doing for this next half an hour. After that I'm going to jump into integration or differentiation. I think I might do an integration question because I haven't actually touched it yet. Okay, cool. So what we've got here is z5 minus 1 equals to 0. So we're going to write z5 equals to plus 1. And because z5 is equal to plus 1, we need to write this in a polar form. So 1 right now is right there, which means we can say z5 is equal to 1 cis 0. And we use Morris Theorem, so z is equal to 1 cis 0 to the power of 1 over 5. Which means our first root is going to be 1 cis 0. Because 1 to the power of 1 over 5 is 1. And then 0 times 1 over 5 is just 0. Now remember, this is the trick that I tell people to kind of work with complex roots. When you have z5, which means you've actually got 5 roots. So what you do is you go 360 divided by 5, which equals to 72 degrees. So that means every root you got to add 72 degrees to it. Luckily, we're starting with z1 with being 1 cis 0, which means z2 is going to be 1 cis 72. And because I'm just super lazy, I'm just going to write 1, 1, 1, cis, 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 144, 216, and then 288. So those are my answers for a merit right there. Merit, that's for merit. If you want to do it by pi, I think it's 2 pi over 5. Yes, you could do 2 pi over 5. No, indeed, you can actually do roots questions in yeah, you can actually do radians or degrees. It doesn't really matter. But that's how fast you can do it with degrees. That's why I like using that with degrees. Abigail, so if you think about it, if you were doing this in radians, right? So radians is 2 pi over 5. Then your first answer is still going to be 0. Your second answer would be 2 pi over 5, then 4 pi over 5, then 6 pi over 5, 8 pi over 5. Depends, Eugene. Like, it really depends on the question. Like, if you're dealing with yeah, it's hard to say, man. Like with roots question, just go with degrees. It's easy, works well. But see, I stop at Z5 because like after, if I do 288 plus 72, I actually end up with 360, which is the same thing as saying 0 degrees. So you're kind of starting on that cycle again. Yes. Okay, now for the second part of the question, it says, what does it say? Let P be the root in part 1 with the smallest positive argument, all right? So this is the second part of the question I'm looking at. So P is the root in part 1 with the smallest positive argument. So if you look at the smallest positive argument, it's going to be this. So we can say, so this is part 2, P is equal to 1 cis 72. Then it says show that the roots in part 1 can be written as 1 p squared, p cubed, p4. So what I'm going to do is I'm going to take p, if p is that, right? Then I'm going to show what p squared is. P squared is going to be 1 cis 72 to the power of 2. And what I end up with is, according to Morris Theorem, this is equal to 1 squared cis 2 times 72, which equals to 1 cis 144. And what you'll see is this entire thing is equal to the third root there. And then if I write p cubed, I'm going to get 1 cis 72 to the power of 3, which means p cubed, same kind of rules, 1 to the power of 3 cis 72 times 3, and you get 1 cis 216. And what you'll see is these things here is equal to this. And then finally doing p4, I'm going to get 1 cis 72 to the power of 4, which is 1 to the power of 4 cis 72 times 4, which is 1 cis 288. And what you'll see is that this is the last root there. And finally our first root was 1 cis 0. Cis 0 is just 1. So 1 cis 0 is going to be 1. So then our roots are 1, p squared, p cubed, and p4. So we've literally just shown how we get the roots are, those are the 5 roots that we actually end up with. So Indy Bear, this goes to Morris Theorem. So Morris Theorem is, let me just screenshot it and then it'll make sense to you. The Morris Theorem is actually given to you guys in your exam. I just need to find where it is. There it is. There we go. That's why I'm actually multiplying the angles. I'm actually putting power of the angles, but I have to actually multiply the power to the modulus, and then for the angles I've got to multiply. $2015, I think, Rory. Yeah, so this is why I do 72 times 3 here. Let me put it the other way around. So if I do 1 cis 72 to the power of 3, then this is 1 to the power of 3 cis 3 times 72. Okay, the reason I chose p as 1 cis 72 was because if you go back to the question, see the part that I've highlighted. It says right here, the one with the smallest positive argument. So 72 is the smallest argument that's positive as one of the roots. So that's why I put p. Yeah, Jacob, I have to say it is a strange excellence question because it is probably one of the really odd kind of excellence question where it just works out real nicely. All right. Integration 2017 1E is what I've been requested. Hey guys, I know some people are still sending me some questions, but if you could, I would really appreciate it if you could actually just flick me either where the question is from or just a screenshot of the answer, because I realize that time is very precious right now and I don't want to be wasting it trying to figure out a question for 20 minutes. So I've just replied back to some people. So if you guys could actually just screenshot the answer, I'd really appreciate it. Dave, I saw your question. Just give me a second. Yeah, so just sending back some questions back, just requesting for answers or just where the question is from. Okay, 2014 1E. Thomas, you just sent me a question for px and px squared. I think I've actually done that question before in one of my Calculus Daily videos playlists. Just have a look, man, because it's back from 2014. All right, there's another integration question that I want to do, guys, which, yeah, I had a look at that, Dave, but I think I need to kind of play around with it first, and I don't want to waste time, so. Yes, Daniel, later tonight after my kid goes to sleep. Okay, I want to have a look at this integration question here, which kind of popped up. And then I'm going to finish off by doing a real quick complex number here. Cool, so this is the question that's been given. It's like find the shaded... Oh, does it, Dave? Okay, I'll have a look through it, man. I might actually start with that question with tonight. And Thomas, if you can't find that question in that playlist, because all the excellence questions, they're like every 5th video is like excellence edition, so there's like all just excellence questions. So in the descriptions, I've actually listed which questions I've actually done. Let me just, give me 1 second. I'll see if that page is updated or not, because I know I'm kind of working on my website at the moment, but just too much to do. No, I haven't finished it yet. That's the problem. Complex numbers, differentiation. Yeah, I'll have it ready next year, but not this year, unfortunately. Yeah, no, the page is not good to go. It's a bit sporadic all over the place. Okay, so let's actually, I'm not sure where this question is from, but someone sent me the kind of the answer just in case we don't get kind of sidetracked. So all we got to do is we got to try and figure out what the shaded region is in this particular question. I was having a look at it before and it was kind of annoying me because the way I was doing it was just a bit too complicated. But it's all right. We'll have a look at it. So the first thing we got to do is we got to try and figure out what that point C is, because that is going to give us a few things to kind of work with. So that's the first thing we want to try and do. Because what I'm going to do almost is I'm going to split this up into 2 shapes. All right. So the first step is to actually try and figure out what this point is. Then what I'm going to do is my first shape is going to look like this here, where this is A and this is C. I mean, this is just, there's like so many ways of doing this, guys, but I'm having a look at the answers, and yeah, that's one way of doing it. But then the other way of doing it is like we could actually do it this way as well. So we could figure out what the shaded gray part is there. And then we could actually go, the second part of this is, it looks like this, from C to B. So remember, when we actually integrate and find area under the curve, we're going to find the red part first. All right, so just bear with me. First thing we're going to do is we're going to try and figure out what that question mark is, and then we're gonna try and do that. All right, so to do that, what we have is sine 2x equals to sine x. And I think straight away some people are going, geez, I've actually got no idea of how to do this, or I've never done it before. Well, remember, anytime you're working with sine 2x, you got to use the double angle formula. So when I'm using the double angle formula, I'm talking about in your, give me a second, I'm just going to find that double angle rule. Where is it? There we go, double angles. We're going to pick this double angle up. Okay, so the reason I have that is because I want to replace this with either, well, sine 2x. I'm just going to replace this with 2 sine x cos x equals sine x. Rearranging this, I'm going to get cos x is equal to sine x divided by 2 sine x, and then cos x is equal to a half. Straight line AB minus both the parabolas from it. Yeah, but the problem is it is not a parabola in D, so we still need to use the sine x. Yeah, I get what you're trying to do, but you have to subtract the area twice. Yeah, as Kiwi Gamer is actually saying. Hyper, yes, they do give the entire formula sheet for you, so you're all good to go. So cos x equals to a half. We can actually go into our graphics calculator and just figure out what x is. Somebody asked me before, when is it a time to actually use radians or degrees? So in this case, I wouldn't use degrees, because if you look at the graph, it's actually given in pi. So I'll actually be using radians for this. So x is equal to 1.047. But also, if you guys are comfortable with what's happening here, you could also just do, what is it? I know what the answer is. I'm just trying to figure out 180. How do you convert radians into degrees? So you multiply it by 180 over pi. I always mess it up and then I go back and do it, even though I've done it hundreds of times. So there you go, it's 60 degrees, right? So instead of writing 1.04, you could write it as pi over 3, because pi over 3 is 60 degrees. So we're going to work out what these two red colored zones are. So for the first one, we've got it between pi over 4 and pi over 3. And that's sine 2x. So basically what we've got here is we're going to work out the red zone. So the red zone actually looks something like this, which is integral between pi over 3 and pi over 4 of sine 2x. And what I'm also going to do is I'm going to kind of put this all together just because it just makes it a bit faster. And our other red zone, because remember we've got to add both of them to get the two red zones. Our other red zone is equal to, that's going from pi over 3 to pi over 2. So pi over 2, pi over 3, and that's sine x. Sorry, Indy, basically all I've done is I've done this. See the sine 2x is equal to 2 sine x cos x. That's all. I've just changed it using this. So I hope you're okay with that, Indy, but we're going to keep going with this. So once we have this, then we can actually integrate sine 2x. When we integrate sine 2x, we are going to get cos, and I'm going to show you guys a real trick here just to make things a little bit faster for you guys. What you could do is this, cos 2x, so it's going to be negative cos 2x over 2 between pi over 3 and pi over 4 plus, when we integrate sine x, we're going to get negative cos x, and that's between pi over 2 and pi over 3. You just need to show this part of the working, all right? Because the remaining part, you can actually do it in the calculator straight away. And so to do that, I go into option, calc, integral. So I want integral of sine 2x. So I'm going to go sine of 2x, but make sure I put 2x in the bracket, between pi over 4 and pi over 3, which is the top number. Okay, and I put it equals to 0.25. So that first part is worth 0.25, and then the second part is integral of sine x, and that's between pi over 3 and pi over 2. That's equal to 0.5. So my total red area is 0.75. So now to figure out what the shaded blue area is, I've got my rectangle. So there's my rectangle, and there's my 2 points. And then the red shaded region there is worth 0.75. So if you have a look at the base and height of that rectangle, right? The base is, because this is pi over 4, pi over 2, and the height is going to be 1, because anytime you have a sine graph, it goes between, and if it has an amplitude of 1, then the highest point it goes to is 1. So I can find the base of this rectangle, which is pi over 2 minus pi over 4, which is another pi over 4. So area of this rectangle, this big rectangle, base times height, which is pi over 4 times 1, minus the red area, which is 0.75. So we can say blue area is equal to the big rectangle minus the red shape there. So putting this in the calculator, we are going to get all clear, pi over 4 minus 0.75, and you should get point. I'll find out, man. Give me a second. So what was it? 0.035. Okay, correct integration for, really? I doubt it. I don't think correct integration is going to get you guys. Correct solution with correct integration is excellence. So excellence for the whole question. Okay, I'm going to come back to you, Indy, on that 1 second. Would finding just the red area get you achieved? Nah, I think you would probably get achieved before that, Hyper, because it actually says correct integration. I know the schedule is a bit wonky here that I have. Correct integration. It just says correct integration is actually worth a merit. And then complete solution with correct integration is excellence. Or at least I think that's what it is. I hope this is not a merit question. Yeah, Indy, if you're struggling with that part, then what you could also do is, as Dampier is actually mentioning, you could do something like this. Go into your graph mode and just put in sine x and then put sine 2x. Draw it and then just go gsolve. look for intersect, and right now it's going to give you all those intersects. Like right now you can see that, see this little plus sign, it's giving all the way there. You want the first point where they intersect right there. So if you just keep going, keep clicking on right button, and there you go, there's that point right there, which is 1.047 as we got before. Yeah, now I would say it's an E question, man. So remember 1.0047 is that pi over 3 as we did before. Yep, you could do that as well. So we're going to set window here because we can actually change x minimum to 0. And I think the question itself, our question went from 0 to pi over 2. So because it went to pi over 2, so I'm just going to put that as pi over 2. And you can kind of see that, but let me just change the view window to y minimum to be -1 and +1. So there you go. Now if you click on Gsolve, it gives you that second point there, which is 1.047. So it's another way you could do it as well. Yep, indeed. So you can actually get the point from the graphics calculator. You don't need to prove how to get those values, but always remember, indeed, you want to get that first value after 0. Okay, guys, it is going to be 4:30 very shortly. Did you just know that 1.07 is equal to pi over 3? No. I'll show you guys how I got that pi over 3 real quickly. Here we go. In your formula sheet, you're given the special triangles. I'm just going to show you real quickly. So somebody asked me, how did I get that pi over 3? Because cos x, so this is what it was, right? This was what the question was. The question was cos x equals a half. So if you look at it here, cos x equals to a half. Now if you look at these two triangles, they are always given to you in your formula sheet, and that's something really useful to try and kind of look at. Now if you look at cos of the angle, that's going to be, so 2 is there, which is the hypotenuse, 1 is adjacent. That means this is what that angle is going to be, and as you can see, that angle is pi over 3 or 1.047. So there's certain numbers that you kind of remember, like 1 over 2, and if you're working with 1 over 2, because if you think about it like this, sine of x equals half, then sine of x means opposite over hypotenuse. That means this is that angle. So this would be x is equal to pi over 6. And remember how we did that complex number question earlier, where we said that if the argument is pi over 4, we go with imaginary equals to the real part. That's because if you look at it, there's the real part which equals to 1, and imaginary part is also equal to 1. That's how we know if we're working with pi over 4, it's 45 degrees, and we're working with an isosceles triangle, that means real part equals imaginary. Alright guys, so basically I'm gonna stop the stream in a couple of minutes because it is getting to 4:30 and I need to go do a few more errands around the house, but I will be, why is it pi over 4 minus 0.75? Okay, to go back to that, hyper, the reason it's pi over 4 is because pi over 4 is the area of this rectangle here, and the reason I got pi over 4 is because my base is equal to pi over 4 and my height equals 1. Oh, there's not really Kiwi Gamer. I mean, like, we're talking about level 3 calc, man. There's just so much things to cover. But I have done some questions that keep coming back again and again. So have a look at my tutorials playlist from last year for calculus live stream tutorials. There's some really questions that come through real quickly. Guys, don't stress about Patreon and Super Chat or whatever. I will I'm gonna come back in about 4 or 5 hours time. I just gotta do a few things. Yeah, so we'll talk. We'll do a few more questions later on. But I still got a list of like I've got a few questions that I still need left to do. So I'll come back at around 8:30, 8:45 and just work till about 10 because I'm not going to go past 10 today. Shot NASA. Yep. Don't stress about Patreon or anything like that. My only thing is like sometime in July I'm gonna come and bug you guys for something. This is actually one of my kind of goals for the next my next year. But yeah, I'd probably would appreciate some help for this later on in July. But apart from that, I will catch you guys later on today. Alright team, signing out. Make sure you guys get some yeah, Dampier, you're like what? I feel sad, Dampier, but it's like as if I've been teaching you for like 3 years now. You and what was that other guy in your class? Was Air something was in your Northcote College as well. No worries team, I shall catch you guys later tonight, alright? But yeah, make sure you get some rest as well. Take like a 1 hour break and then, not a 1 hour break actually, who am I kidding? Take a 20-minute break and then get back to it guys. And I will catch you later in the evening. Oh no, you're not, sorry Dampier, apologies. Yep.